Okay, so today we are going to cover infrastructure as code. So what is that? Well, actually, before we cover infrastructure as code, I have homework number 3's histogram. Well, actually, Leslie created this. She kept track of the container size of every single container that people submitted. And if you're all the way down here, that means you're under 20 megabytes. So the smallest ones, there were basically around 6 that were below 20 megabytes. And for those 6, Jason, Barb, Jordan, Micah, Jesse, and Kevin, I have some YubiKeys to pass out. Hang on a second. So yeah, those are really small containers actually. So I bet you those things deploy pretty fast in the cloud. I did want to briefly go over some of the techniques. They were linked. I had those articles linked at the end of the homework if you wanted to explore. This is sort of a rundown, and any of the 6 that I've just given YubiKeys to, if I've missed something, you can shout out some other things that you've done. The first is starting with a tiny base image, Alpine, or maybe the Python version of Alpine. I think everyone was using just Alpine and then installing stuff afterwards, because there's some stuff that gets added to this that you might not need. The other strategy is to use as few layers as possible, so having a single large run line with all the commands in it. One monolithic, horrific line, basically. The other thing is when you do the install, so pip, when it does this installation, it's trying to cache some files, so if you pip install something else, it has some of those files locally. You're only ever doing one pip install in your Docker container, so you don't need any caches. This is just a one-time pip, no caches. So that's another one. Yeah. The other. This is your Docker file. So all of these commands are in your Docker file. So you notice run, run. This is, you would have from, what is the command for specifying the base? It's from something or other. Yeah, so these are all Docker file commands that we're talking about. So yeah, the Docker directive, it's missing there, but it's there. So those are 3. The other one is to delete all of the unnecessary files, and this is where you really got to be sort of anal retentive about all of this stuff. You just got to keep on trying to remove stuff and see if it breaks. And like, oh, that didn't break. I'm going to remove something else. And then, ooh, that broke. Oh, let's leave that in there. But that is, I would imagine, a lot of manual trying. It's like, what the heck is this directory? I'm going to remove it. And then, of course, your thing doesn't come up. And so here are some examples of things that you don't need. So like APK deleting the build dependencies. So, yeah, this was hilarious. I laughed when I saw this. Removing requirements.txt, because you never know when those 50 bytes might get you a YubiKey or not. So that was pretty hilarious. That's the first time I've ever seen someone delete requirements.txt in a Docker file. So I got a good laugh. When you install, you can install pip. So if you have Alpine, so Python has pip in it, the Python base image. But if you start with regular Alpine, you can install pip, do the package installation, and then uninstall pip. And then you get rid of that from the base layer. So some people did that, all in one layer, of course, because otherwise pip shows up in your container. Not updating the APK and then adding a Docker ignore. So this is an easier way of just saying, hey, you know what? Don't put any of these files in my container image, and then let me see if the thing still works. Did I catch most everything, or did someone want to share another hard-earned savings of bytes from their Docker container? Yeah. Yeah, that was this. So there's multiple ways. So pip does some caching, and I think apt does some caching, and APK does some caching. So then you would have to see any of these tools that are installing software. If they're installing any files that you don't need after the installation, you want to remove all of those, and you want to remove all of those in one enormous line, like this one. It does the entire line in one. Yeah. Mm-hmm. Yeah. So if you do a multi-stage build, You could use the regular Python dev base image, and then when you have created your app, you just copy over the binaries into a Alpine image. And this is one line, but you have to know exactly which files to copy over. And then you can keep all that installed stuff in that first stage. And then in the second stage, you're just copying over the code that is used for running. This is similar to that unikernel approach, where you're like, hey, I don't need any, I only need, a certain subset of the base distribution. I'm just going to copy those directly into an image. So. Yeah, which is a pain. You have to really want that YubiKey to go to that level of understanding what parts of the Python hierarchy, what parts of the library you actually need, and then the ones that you actually don't, that you can actually remove. So, well, then you have a bigger container image. Oh, it'll work, but it might not get you below 20 megabytes. And if one of the 6 of you want to actually share your Docker file, I won't be able to share it, but if you could post your Docker file and say, hey, this is the one that I used, then everyone can sort of see the kind of shenanigans that go on with making a really dinky Docker container. Yes? Not that anyone use anything other than Alpine as a base? Nah, I think Alpine ended up, I think there's BusyBox, which is also something below that, but that's really painful to build up from BusyBox. But I think Alpine is, at 20 megabytes, there is a law of diminishing returns. And when you get down to 20 megabytes, how much is it worth, that last 1 or 2 megabytes? I probably need the deluxe YubiKey for you to do that. But this one is the low end one. So, okay. So back to infrastructure as code. So what is this? So far in this class, in the cloud part of the class, we started out with server-based systems, infrastructure as a service, where you're actually managing the low-level machines, the web servers, the operating systems, the networks, and if you have a large website, you're managing all of these things manually. This is good if you need the flexibility, and you need custom hardware, and you need a lot of customizations in your runtime. But it's really bad for management costs. Some poor soul, an ops person, has to go around and manage all of those machines. And if stuff goes down, they have to go back over there, start up a new instance, and then install all the software and get it back up and running again. So this is very time-consuming, and it's very error-prone. People are making mistakes deploying this kind of stuff left and right. And then on the other end, we have completely serverless systems, which is what your homework number 4 should have shown you. I can just write my app, and then everything, storage, databases, the platform, the container, the function, all of this stuff can be done serverlessly. And I don't have to manage any of that stuff. So I write a program, I deploy it to an auto-scaling platform. The front end is auto-scaling, the back end auto-scales. I don't have to touch either one, and it'll do it. And so this gives you this infrastructure is now abstracted out. I don't get to see it. So there are no management costs in this model, but it's not flexible. I am beholden to what App Engine decides to scale up and down for me. The policies that it wants to employ for starting up an instance and setting new instances up based on load. I have to take what App Engine gives me. So you have this very coarse control over how to scale the architecture and the infrastructure. And then I also have, because underneath this platform is running on a specific set of containers, I typically am fixed to a kind of operating environment. So if I have a lot of crazy customizations in my containers, for example, these platforms don't want to handle me. And they're like, I'm too high maintenance. I'm going to go somewhere else. So what is infrastructure as code? You want the benefits of serverless. You want automation and low management costs at runtime, but you want the benefits of being able to have access to low-level server resources. So I want to be able to do some performance optimization. I want some flexibility in how I allocate resources. So for example, on a cloud function, if I don't use that cloud function, it basically idles, and it goes out of, it basically gets stopped. The container that services that function gets stopped. And then the next time someone accesses it, I have this cold start delay. If I don't want that, then I can't use that Cloud Function service. I need to do something else. And that something else could be, hey, maybe I'll run a container that has all of my functions in it, and I'll run just one instance, and then have that thing up and running all the time. Okay. So how would you do this? You want both. And so the idea is to use programs or code to create, configure, deploy, and manage your virtual machines and your containers. And this is basically create your own serverless architecture is what you want to do. I want to create my own app engine. I want to create my own Cloud Function service. So this is basically what we're talking about when we talk about infrastructure as code. And if you recall, software-defined networks, where you're programmatically configuring the routes and the virtual networks and the traffic engineering to basically implement the networking for your cloud project, this is the equivalent, but it's done using the machines, collections of machines, okay? So the IAC is the SDN analogy for virtual machines and containers. You can think of it as that way. It also does networks, but we'll get to that later. Okay, so for an IAC system, there are two pieces to this. There's the configuration management, which is setting up the images that you're trying to run, and then the deployment management, basically deploying all of these things onto actual infrastructure, and then the runtime orchestration, making sure that all of that stuff is running. So yeah, specification and configuration, the first step, and then the runtime deployment is the second step. Okay, so there is IAC for virtual machines, and so the way the cloud started was AWS had basically their EC2 service, and it was just a bunch of virtual machines. And so things like Ansible and Terraform and all of these companies were like, hey, I got hundreds of EC2 virtual machine instances. I don't want to go and manually configure every single one of them. And so these systems, so Vagrant, Ansible, Chef, all of these things were basically deployed to try and make the management of all your virtual machines automated, or more automated. Locally, there's Puppet, and they started with a declarative approach. So there are two kinds of IAC for virtual machines. There's this imperative scripting language approach. This is basically like system administration, where you're doing it in a scalable fashion, where like I'm going to run one command and send it to all of my virtual machines. But I'm doing this imperatively, command by command. The approach that Puppet took was to say, you know, just declare a specification for what you want running, and then I will build a runtime that tries to meet that specification. So this is sort of like regular imperative programming, and this is like functional programming, or on the second method. And then some of these things will do both. So that's for virtual machines. And then the deployment management, the orchestration piece, is to actually get this stuff into your back-end infrastructure. So something like Terraform, we'll take that, we'll deploy all of that infrastructure, we'll do the runtime monitoring, and then keep all of that stuff going over time. So you might see some of these tools in whatever job you might get if it involves the cloud, and that's what it is. And so Terraform is this multi-cloud tool if you have deployments on multiple vendors. But within a single vendor, you have AWS has this CloudFormation service, and then Google has their Cloud Deployment Manager for doing something similar, but this definitely is targeting a specific provider. And if you have noticed, in the both in the CDN lab and in the Thunder CTF, we use the Google Cloud Deployment Manager to instantly spawn all of those resources so you could do those labs quickly. So you're not manually deploying any of the infrastructure in these levels. So they're using both of those. Okay, so just like there is IAC for virtual machines, there's IAC for containers. And again, it has the same two pieces. It has the configuration management. And basically, we just covered the configuration management. They're Docker containers. That's basically how we're installing all this different software on the nodes that are running it. We're just creating a Docker container, and those are the building blocks that we will then deploy into a backend that has a bunch of containers running. Deployment management and the orchestration is not what is something that we haven't covered. And so the idea here is to automatically configure, deploy, and monitor clusters that are running collections of containers. So that is what today is going to be about. Okay, so there are two pieces to container orchestration. There is the specification, which is a programmatic way of describing what you want to run. And this is going to be in a YAML file. And you actually sort of saw in App Engine's YAML, that's basically what this is. It's a declarative way of specifying what you want App Engine to produce for you. So that's an example of this. And in fact, this thing probably maps to what we're going to cover next. The other piece is a runtime daemon, which is an orchestration controller that is sitting there monitoring all of the infrastructure that you have asked it to deploy in order to keep the thing running. Okay? So here's an example of a specification with the runtime monitoring. Say I want to run n copies of a service, of a container, and I want it to autoscale based on a metric. In my specification file, I can specify a policy that's this, like run 10 versions, or keep adding containers until the load on each of the container is under 0.5. And then you would want the runtime to implement that. You can have in your specification all of the network connectivity associated with it. So if you only want to enable network connections from one set of resources to another, and you don't want to allow any other connections, then this is a way of specifying some of the security properties of your deployment so that you make sure that if you get compromised, the adversary can't do just arbitrary things into your backend. The other piece of this is the daemon. And the daemon is sitting there reading the specification in, and then it's conspiring to always meet those specifications. So if you launch a set of resources from this configuration and you start deleting the resources manually, you'll see that the daemon is like, hey, those resources aren't there anymore. I'm going to start them back up again. And so some of you saw this with the WordPress stuff. When you were doing the marketplace deployments. If you went to the marketplace and deployed 3 solutions, and then you went over and you saw the virtual machines that were running these solutions, and you're like, hey, I don't want these things to run. I'm going to delete each one of these virtual machines. What happens is, yes, those 3 machines get deleted, but then the deployment manager is like, oh, you asked for 3 of these deployments. I'm going to restart all 3 of them. And then that's where your coupon goes to 0. So I would imagine, I think 1 or 2 of you had this, where you're like, I didn't know I was running those 3 virtual machines, those really 3 expensive virtual machines, the N1s. And I don't know, maybe it's a problem in the lab. I should have really explicitly said in the lab to go back into the deployment manager, and you have to kill the deployment. Because the deployment is there still, and the deployment is like, oh, you really wanted one instance to be running all the time. And so you have to kill the deployment, not the individual thing that's implementing the deployment. Okay. So one of the initial examples of this was in 2003. Google had this thing called the Borg. And this was an ops tool to do exactly what I just mentioned. It had a declarative programming language to specify what it needed to run and how to run it. And then it had a controller piece that is going to take that specification and then monitor and maintain the infrastructure to meet that specification. And what this does is that now the application developer doesn't have to worry about deploying machines, which is what you don't want. The application developer is good at developing applications, not necessarily good at managing all the different parts of the infrastructure. Okay. So this got re-implemented and spun out as an open source project called Kubernetes. And Kubernetes is what we're going to work on in this class. So this piece of software has implementations on all 3 of the major providers, Google, AWS, and Azure. So this was developed in 2014. It's a container orchestration system, and it's basically a re-implementation of Borg in the programming language Go. And so you can think of this as a deployment manager or a cloud formation, but for containers instead of virtual machines. And this is an open source project. It's managed by the Cloud Native Computing Foundation. And because it's open source, a whole bunch of companies are like, I'm doing this because I don't want to get locked in to Google or AWS or Microsoft, because each one of these places have their own custom version of this functionality. But as soon as Google spun this out to the Cloud Native Computing Foundation, and now it's managed by a consortium, they're like, okay, everybody just do this, is effectively what happened, which is why I'm teaching it and not something else here. Okay, so what is Kubernetes? This is a whiteboard level specification of computing infrastructure. So if you go to the whiteboard and say, these are the services I want, like your guest book, I want, here's a box for Cloud Data Store, here's a couple boxes for my front end, that's basically what Kubernetes is asking you to specify. And then you give it that whiteboard specification, and then the runtime is just going to sit there and try and execute that specification. So it's basically a custom platform as a service done via a YAML file. And it turns out the programming language you really need to know the cloud is YAML, unfortunately, because YAML drives just about the configuration of everything on the back end now. And we'll look at the YAML file in a second. And so one of the things to think about is that the traditional platform as a service, we call that opinionated. So Google has some default settings, and they are enforcing their opinion on what should be run in their App Engine system. So this is not opinionated because you get to decide what gets run. You have more control over what the policies that you want in terms of infrastructure management. Okay. So here's an example of what's going on. Here is the daemon. It's the master control plane thing. And this is the thing that Google or AWS or Azure will run for you. So rather than you having to set up the daemon, they'll be like, you know what, we'll host the daemon, because that you don't have to worry about configuring that. You just give me a specification, and the specification will go to this daemon, and the daemon will sit there and spawn everything. So that's the model. And then the daemon is going to spawn different nodes, and the nodes are going to have different container images. They're going to have different networking set up to get the whole thing to work. Okay? And basically the daemon is going to do the self-healing, the auto-scaling, and this thing is portable because it's all open source. This thing is abstracting away the sort of the lower level differences between the cloud providers. Okay, so this thing manages all of Google services. All of those services are managed by Kubernetes. It's used by Uber, Bloomberg, Lyft, New York Times, eBay, pretty much half of the Fortune 100, and this was in 2018. So yeah, this is last year, and about half of the Fortune 100 companies are using Kubernetes to manage their back-end infrastructure. Here's another article. Cisco and AWS are pairing up on Kubernetes management. VMware, the king of virtual machines, has decided maybe virtual machines might put me out of business. So now they are also in the container business, VMware, and they are also going all in on Kubernetes. I have more of these. Microsoft has embraced Kubernetes. So they're actually deprecating their proprietary container service, their Azure container service. And they're launching a whole bunch of projects on Kubernetes and microservices. Okay. And this is really just another attempt to raise the level of abstraction, but to raise it in a way that doesn't give you total loss of control over the infrastructure you're providing. So this is a quote from Eric Brewer, who's the guy who made the strategic decision to open source Kubernetes. And this was in it was in 2014 or 2015. He made this decision, and this is a quote from last year. And so the model is that the cloud is too focused on the actual machines and the disks. And what they want to do is to pretend like none of that exists at all. So basically more of a serverless style. And this is what Kubernetes is trying to do. And so the Kubernetes is allowing you to focus on services and APIs and then not worry about infrastructure underneath. And so when we're going to be working on a bunch of API stuff for the next part of this class, all of that stuff on the back end is likely being done and serviced by a container managed by Kubernetes, is the implication. Okay, so Google is going to manage that infrastructure for you, and then as a developer, you shouldn't need to know any of that stuff is going on, eventually. So here's an example. Here's a picture of a Google data center. And so if you want to run 10,000 copies of your website of Hello World, you could manually SSH into there and then start up 10,000 copies of Hello World. Oh, I don't have the animation. That's too bad. But what you would do instead is you would automate via specification. So this is the job, and you say, hey, this is the machine, my machine requirements that I want it to run on, and then the number of replicas is 10,000. And then if I give this to Kubernetes, then you would get basically, over time, you would get the number of running tasks would eventually get to 10,000, and you'll see that this thing is automatically deploying your Hello World to 10,000 nodes in this data center, and you don't know which 10,000. Yes. This is in seconds, so yeah, you can't. And actually, up here, what's hilarious, if you zoom in here, it never really ever gets to 10,000 because the mean time to failure is such that the thing is like, collections of nodes are always going down because you're at a scale where you'll never hit 10,000. You're always, something is always crashing on the back end. But you don't care. You don't care about those crashes because you have auto-scaled your service to 10,000. Yeah. You could try doing this on your coupon and then measuring it yourself, but your coupon won't last very long. Okay, maybe at the end when you blow out your coupon, you'll see if you can put 10,000 nodes up. There was some university that tried to, I think it's something like Georgia Tech or Georgia, they tried to bring up the largest compute cluster ever recorded, and then they basically did one of those. Like, I'm just going to allocate everything in South Carolina or wherever that data center is, like 10,000 nodes. But yeah, you'd have to get a lot of money from Google, and I didn't ask for that much. Okay, so some concepts with Kubernetes. The first thing is a node, and a node is a virtual machine that is going to run your container. So that's a simple, straightforward thing. It's a compute engine instance. And then you have pods. Pods are logical collections of containers. So that these pods will be mapped, individual pods will be mapped to a node. A node could run multiple pods. So an example of a pod is that maybe the web front end of your site and a logging facility that consumes the logs of your website would be co-located in a single pod because they logically relate to each other, right? They're always deployed together in pairs, so you would put them in the same pod. So that's the idea. And then from this collection of pods running on nodes, you want to export services. So this is, everything is running behind this Kubernetes cluster, but then you have to actually export an endpoint that someone can access. So for example, you have maybe 10,000 pods for 10,000 Hello Worlds, and they want to, the service is, I want to export one website, one logical website that is a front end to all of those 10,000 backends. So in my service definition, I have port 80 on some load-balanced IP address is my service that I want to export, and then it would spray all of the requests into the 10,000 pods running in the back end. So that's the other piece of this. Okay, and then finally the controller, which you never see because, and I would never recommend that you try and run the Kubernetes controller on your own because it's a lot of configuration stuff that's basically really hard to get right. You want that thing to be run as a managed backend, and that's what the controller, that's what GKE and AWS's Kubernetes service is going to do for you. Okay, this is what it looks like pictorially. So you have the control plane, the controller, and the controller has your YAML file. So you'll see that all of this gets specified in a YAML file, and what you do when you run the kubectl command, it's basically going to send your YAML file to the controller. And then the controller is going to read your YAML file and be like, oh, I have to deploy all of this infrastructure. Then what it does is it spawns off. So the other thing you have to do is specify the nodes. Say I want to have 3 virtual machines run my containers. Then I'll say, hey, bring up 3 virtual machines. And then for all of the pods that I specify in my YAML file, map those into the nodes that I have given you. So you have a computing cluster, and then you have a YAML file that maps the containers into your computing cluster. And then you can see that each one of these nodes has a bunch of pods running. And then there is a container runtime and a kubelet runtime that is sitting here doing a bunch of health checks, right, to keep the whole thing up. Because you have to keep this, based on the specification you gave Kubernetes, it has to make sure that it faithfully keeps all of those machines up so that nobody has to carry around a pager anymore on the back end. Okay, so here are some interesting, fun resources for learning Kubernetes. The Illustrated Children's Guide, a cartoon, I think this is my favorite, just a cartoon comic strip version of what the terminology means and does. And then there's this video that shows you a Minecraft UI. Just like the Minecraft UI for Docker, there's a Minecraft UI for managing Kubernetes clusters, which is, I mean, if you're having a hard time getting your head around what Kubernetes is doing, I would watch those things. Okay, because it's not easy. This stuff is not easy. I mean, that's why they have comic book versions of this. Because like when you start reading Kubernetes documentation, you'll be like, oh, I don't want to learn any of this stuff. This is like way too obtuse. But okay. So assuming that you're using a hosted Kubernetes service, your commands will be as simple as something like this. kubectl, create a deployment, and then use this YAML file as input. And the YAML file is something that looks like this. This is the YAML file that says, I want Kubernetes version 1. I'm specifying a pod. And in that pod, I'm running this image, this container image. I want you to run this thing on this pod. And then the port that the thing is going to listen on is 8080. And so this is specifying the thing that goes into here, right? This specifies what is in the pod. And then based on this, then the other thing you'll do here is create a cluster, and then this thing will map the pod into your cluster. Okay, so case study. Does everyone know what that is? Pokemon Go. Do you all play it still or no? No? Oh, someone plays it still. I still see people in the middle of a park doing, like, all pointed at each other to, like, what is this collection of people doing together? All ages? You're like, what's going on here? And then you sort of look and you're like, okay, they're playing Pokemon Go. So that's what this thing is. So this was published by Niantic, and it was a augmented reality startup company that was spun off from Google. So Google Earth is sort of their whole world simulation stuff. So they had a subset of engineers that wanted to build an augmented reality sort of experience. And so they spun off Niantic, and it was basically this app called Ingress, which is sort of augmented reality on top of the real physical world is what they were doing. And their idea was to build a game that had a single shared virtual world overlaid on top of the real world. And then Nintendo approached them saying, hey, I want you to build something that has Pokemon Go as part of that, and that's where the game started. The world state has to be consistent across all the users. 2 players can't get the same Pokemon at the same time and have that thing be replicated. When everybody's sitting there at that waypoint trying to get that thing, only one person should actually get it, right? For those who play it. Everyone gets it now? Okay, well then maybe they changed the programming to not allow. But typically you would want just one person. But if you're doing this and you want to maintain consistency, you have an n-squared problem. You have a consistent, sort of like the blockchain if you're in the blockchain class. You have a distributed agreement problem where you have to get a whole bunch of peers to do consistent agreement on the state of the world. So this actually causes the computation to increase pretty quickly. They decided to use App Engine to build this app. And then they provisioned the launch numbers to, they basically took the top launches of all the other mobile games, and they multiplied that by 5, saying, that's our upper limit. That's the number of people who are going to play this game. And then they released it July 5th of 2016. And then they ended up surpassing Twitter in daily active users within a year, I believe. Is that one? Yeah. No. This is 5 days after. This is July 10th. You can't see that. This is July 10th of 2016. So within 5 days, they're beyond the number of active Twitter users. And so basically within 1 week, they had 50 times more users than they initially expected. So rather than 5 times, they needed to have multiplied it by 250 times. And I bet you with the launch of this, there were a whole bunch of Google engineers buying pizza boxes, the servers, to feed more compute power into their data centers because there was this huge spike in resource usage on Google's backend because of this game. Okay. And so this scaled seamlessly, and I put a star there. There were some issues. This is a link to the podcast from the Niantic person that talked about what happened during the launch that I recommend you listen to if you have some time. It's built on Java, and then on the client, it's basically C# and Objective-C and those kinds of systems. And then on the back end, they do Cloud Data Store. So App Engine, Cloud Data Store, that's basically what Pokemon Go started with. But what does that have to do with Kubernetes? In this podcast, they're like, yeah, that all works for an initial deployment. But when you get down to this is going to be a long-running service, they found there was some real drawbacks with not having control over all the pieces of the infrastructure running that service. So any kind of performance bottlenecks or delays or overusage of resources, they couldn't get their hands on the knobs that they needed in App Engine to customize it to their purposes. So they ended up shifting all of this over to Kubernetes so that they could get more control over it. And that's what you'll be doing with your guestbook app. Like you have a guestbook app, and you could probably do this with your homework number 4. You have the thing running in App Engine. You're like, yeah, it's a container. You did it on Cloud Run. You've done it on App Engine. You're like, yeah, I don't really want App Engine to manage my service. I can just shift it over to Kubernetes because I got a container. That's what Kubernetes wants. I'll just specify a YAML file, and then you're good to go. So I would imagine it would just take you like a 30-minute shift to go from your App Engine over to a Kubernetes deployment. Another case study is Home Depot. They started out with a single monolithic site with a single database on the back end, and they decided to split this into microservices and migrate it to containers. And the biggest thing is developer efficiency. Because if you're developing and there's just one monolithic site that you develop to, all of the engineers trying to improve different subparts of that site have to collaborate together on a release schedule to deploy things. And so you have things in Home Depot, and this is also a podcast that you can look up. They have a store finder, they have a coupon service, they have a product information catalog, they have their shopping cart stuff. They have all these different services, and what they ended up needing to do is they have to get rid of this centralized bottleneck of having all of that go to a single web development site, a monolithic website. And so they split it up into microservices and containers, and then they have a DevOps team for each one of those microservices. And then they can do Agile on one of those sub-sites rather than having to do it over the entire site. And then in order to manage all of this stuff, they just do Kubernetes to get that thing running. Okay, so some other migrations. So GitHub moved all their stuff to Kubernetes 2 years ago. CCP Games, these are the folks who make EVE Online, which Bart plays a lot, Bart Massey. I think he offered an EVE Online course last year. This is all managed on Kubernetes, their backend. And this is a shared virtual world shared amongst tens of thousands of players. So this is quite an engineering feat on the backend. And so what we're going to do is work with Google Kubernetes Engine. And if you look at this spectrum, we did the thing on the left, managing machines. We did the thing on the right, where there are no machines. We're going to do the thing in the middle now. And that's what Container Engine is. We're going to have a notion of machines, but they're going to be logical. They're not going to be the actual machines that we log into and install things. They're going to just be nodes that I can specify. And I'm going to have a YAML file deploy everything that I need to run my site. Okay. This was formerly called Container Engine. They renamed it Kubernetes Engine because it more accurately fits what they're doing here. Okay, I'm going to skip this and talk about the labs. So your labs, the first one is to, at this link at the bottom, is to practice some of the Kubernetes commands, just to get a feel. And this is a guided tour of the kubectl command set. And then you'll be running these things manually in the lab. And just show the last step after you go through here. The lab that I referred to earlier is to take your guestbook app and to deploy it on Google Kubernetes Engine. So you've done App Engine, you've done Compute Engine, the guestbook on both of those. We're now going to deploy the guestbook on Kubernetes Engine. So that's a picture of what we're going to do. This is the architecture of what we're going to deploy. We're going to specify 2 nodes. So when you create the cluster, you're going to create a cluster that has 2 virtual machines in it. And then what you're going to do in your YAML file, you're going to specify 3 replicas. You're going to specify a pod, and the pod is going to, the YAML file is going to specify that you want 3 replicas of the pods. And so because there's only 2 machines and there are 3 replicas to run, one of the machines will get a duplicate pod. And then as part of the Kubernetes thing, you're also going to export a service. And what this service is going to do, there's going to be 3 versions of your guestbook container. So each pod has a version of the guestbook. And the guestbook is on the back end speaking to Cloud Data Store. Then you're going to have a load balanced front end so that there's only one URL to hit. And when you hit this one exported service, it will automatically route you to one of the 3 pods in this lab. So we're going to walk you through how to specify this, and then you're going to deploy it and then test it as part of this lab. Okay. And then the pod is going to run on port 80, whereas these pods, I think the pod is running on port 8000. So then you're going to see how to map the service port to the individual target pod ports. Okay. So the first thing to do is enable both the Kubernetes engine, and Compute Engine's already enabled, so you shouldn't have to do that, but that's basically what this is. And then what you're going to do is you're going to set up a cluster. You have to specify the amount of nodes that you want to run your pods on, and that's what this is going to do. It sets some of the G-Cloud compute stuff, so we're going to actually put our cluster in US West 2A in this lab. So this is what this configuration is doing. And then you're going to create the cluster. And this is the command for creating a cluster of 2 virtual machines in US West 2A. So you'll be running this command interactively. And at the very end, it'll tell you, hey, this is the cluster that you have. This is the master IP. So this is basically the Kubernetes engine IP address. So the controller is running on this IP address. And then you have 2 nodes over here on the right that are running that are basically idle. There's nothing running on there right now because they've just been brought up. Okay, after you bring up this cluster, visit Compute Engine and then show that the 2 virtual machines have been created. And then also show Kubernetes has created instance templates and instance groups to specify this as part of implementing the YAML file. And then you can see the 2 virtual machine instances that it has brought up. And then what you're going to do is I'm going to start running Kubernetes commands in Cloud Shell, and I have to specify what those commands, what this configuration that I'm going to run, what backend it's going to use to deploy the infrastructure. And that's what this is, config set container cluster to the guestbook cluster that I just created in the previous step is the next command. And then get the code, so clone the repository. There's a directory now. If you don't have this directory, do a pull, because that directory just got created a couple weeks ago. So do a pull, and then view the Docker file. The Docker file is basically exactly the same as the one in Cloud Run, except I actually specify port 8000 as the container port, because I'm going to hard code it, because I'm going to specify 8000 rather than pull it from the environment, like Cloud Run did. And then change the maintainer. And then the other piece, what you have to do is change the data store client to be your project ID. And then what you do is the next step is you're going to be using the container registry. You're going to build the guestbook container, and then you're going to push it up to your local container registry, just like in Cloud Run. In order to do that in the command line using Docker commands, I have to configure Docker so that it can use gcr.io. So this gives the Docker command credentials to upload images to gcr.io in Cloud Shell. And then you just build the image directly. So Docker build, this is the tag, and then the current directory with the Docker file in there. And this builds this container in gcr.io, or it builds it with this tag, and then I can push it to the registry using a Docker push, just like you did before with Docker Hub. Okay, so now I have this Kubernetes guestbook image in my registry, and note the name of it, because you're going to have to use this name in the YAML file when we specify the configuration. So here is the configuration. If you look at guestbook frontend.yaml, actually, I think that might just be guestbook.yaml now. This is the pod specification. So this is the thing that's running those 3 replicas. I say I want 3 of these pods, and then the guestbook that's in there, the container that's running inside of this guestbook is gcr.io, and then your project ID /guestbook, which is, wait, no, all right, that's, this should say K8s. K8s_GB. I think it does. When you clone it, it's actually got the right name when you clone it. It does? Okay. I broke the slide by changing the name. But yeah, you just substitute your gcr.io image name in for there. Is the only modification you have to do to this YAML file. I just wanted to show you this because there's nothing magical here. It's just, so the container port is specified as 8,000, the image is specified, and then I want 3 replicas, so 3 pods will get distributed into my cluster. The other part of this file is the service specification. And so for this, and this is just underneath this in the actual YAML file, I want to specify a load balancer, a guestbook load balancer that is the front end. And what it's going to do is it's going to take requests and then map it to this guestbook app on the back end. And it's going to take a front end port of port 80 and then map it to the target port of 8,000. And so if you see all of these apps here, these pods are labeled by this app name, and then this service definition here is saying take port 80 of the load balancer and then forward it to 8,000 in the backend pods. And that's it. This is the entire Kubernetes file. And this is the thing you should say, hey Kubernetes, run this thing, and then you go. Okay. So then what I do is kubectl, I need to get the credentials to allow me to deploy this onto the Kubernetes controller in my project. So that's the command for interfacing with the GKE to get your credentials. I need to get the credentials so that I can deploy onto the guestbook cluster. And then what I can do is, now that I have pointed my default cluster to guestbook and I've gotten the credentials for it, I can now do the deployment. And so kubectl create a deployment using the guestbook.yaml file, and then that will actually instantiate those 3 replicas, and then I'm good to go. Okay. So if you note, all of this stuff has nothing to do with Google. There's nothing specific to Google in this file. Maybe this thing, but you could replace that image file really easily with something else. You could put a Docker Hub thing in there, and it would work. And so it's really important to look at this and realize that you can take this thing, bring it over to AWS, and run it, assuming they have a Kubernetes, a hosted Kubernetes over there. And rather than using compute engine virtual machines, it's just going to use EC2 virtual machines. And this is the power of Kubernetes, right? I only have to do this specification work once, and then it'll just work everywhere. Because basically the infrastructure is a commodity, right? And I am bringing the value add is a Kubernetes YAML file, is the idea. Okay. After you do this deployment, you do a get pods to see that you have 3 pods running. Do a get services to see the IP address that's been created and the service port that it's exported. So it'll be an external IP address with port 80 is basically your service endpoint. And then you go visit that external IP address, and then you should get basically the thing you've been seeing all quarter long, which is the guestbook entry backed by Cloud Data Store. And then I want you to sign a Kubernetes message into your guestbook. And then what I want you to do is to show the app running on Kubernetes Engine, so you can see the deployment in Kubernetes Engine. Show the load balancer that has been brought up in the network services, similar to your CDN lab. You brought up the load balancer on that one. Show the external IP addresses that have been allocated. And then, so you'll see that each one of these pods has an external IP address, so you can actually access those. And then show the Docker image in container registry and show its size. So that's the end of the lab. You can either delete the deployment on Kubernetes Engine, but that won't delete the cluster. You might also need to do this, delete the cluster. So you could do this from the command line. You first delete the deployment, and then you delete the infrastructure that's running that deployment to clean up. Are there questions about what you're doing? Yeah. I can specify a minimum and ask it to grow in that simple YAML file because I didn't want to confuse the heck out of you. I wanted it to fit on one slide. I didn't do anything crazy in that YAML file, but that YAML file can specify a full-on, a very expressive way of managing the infrastructure that I haven't shown you, just to get you started on Kubernetes. Are there any other questions? Okay. The other thing I want you to do is to go over to AWS. AWS has this proprietary Elastic Container Service, and it's basically going to give you the same thing, but without the open sourceness. So this is their proprietary container service, and it's effectively doing what Kubernetes is doing. It's basically a front end to this back-end virtual machine and container orchestration system that is basically implemented using CloudFormation and this thing called Fargate. And so the idea here is that CloudFormation will deploy your VMs, and then the container service will map the containers to those VMs, just like we had done all by Kubernetes. These things are broken up on AWS. So that's their proprietary equivalent. They were forced to build a ECS for Kubernetes because everybody was like, I don't want to lock into this proprietary ECS service. So eventually the ECS service is probably going to get deprecated. And like you shouldn't deploy new things on ECS. You should actually just use this. But I don't have a lab that works on ECS for Kubernetes, so we're just going to do ECS straight up. Go and log into your account. When you are on your console, click on ECS and then get started. The framework is exactly the same, except instead of pods, they have tasks. So they have the same thing, and then they have a cluster, they have a service that's exported, they have a container definition, and then instead of pods, they have these things called tasks. So what you're going to do is you're going to bring up ECS, you're going to configure a custom container over here in the bottom right. And then I'm going to have you run the OWASP Juice Shop container. And this is an intentionally vulnerable web application that OWASP uses to teach web security. And it's a Node.js app. So you just specify the Docker Hub image name. And that's what this is right here. So you copy that over. You call it Juice Shop, the container image. You click Next. You have to specify this container. By default, will listen on port 3000. So your container, your homework container, listens on port 8000. This particular container listens on 3000. So you have to specify that this container has TCP 3000 that it needs to listen on. You update this, and then you edit the service definition and say, I want to run 2 of these replicas. This is the same thing as replicas in Kubernetes. And then I want to have an application load balancer that will load balance between those 2. So it's a very similar setup as the Kubernetes lab. Click on Save and then Next, and then name the cluster Juice Shop with your Odin ID. Review the settings and then create this cluster. And then eventually, you should get something that looks like this. Now, people were having trouble with this over the weekend. Did that resolve it? Not at all. Okay. If that doesn't work, show the screenshot of it failing. I might need to debug your AWS. Has anyone tried this and it worked? Okay, so a couple people, so it might be, okay. Yeah, AWS gremlins that are, yeah, you didn't make a proper sacrifice to AWS apparently. They have an office over there, maybe you can. Yeah, all right. So I recommend in my blockchain class, do it in the morning when nobody is doing anything. So I have it like at 8 o'clock. Like the stuff seems to work at 8 in the morning better than it does in the middle of the afternoon or at night. Okay, and then what you're going to do is you're going to go and you're going to poke around after, assuming this does deploy for you, you're going to poke around and check out the different parts of this service, similar to the previous lab. And then one of the things I want you to do is bring up the service endpoint, and you should get something that looks like this, where this is, you don't know which of the two replicas is servicing this, but it's one of the two. And then you can hack the site or not. One of the things that you can do in the is to go to the cluster and check out the two running instances. You wanted two replicas. The two replicas are here. You can poke into these replicas and you can see their actual IP addresses. So these are the two IP addresses, and you can go and you can access those things directly via a web browser. So that API front-end web, that load balancing IP address will just forward back to these back-end port 3000 versions. So delete the cluster, and then I want you to repeat this using your HW3 small container. And then instead of port 3000, you need to use port 8000 because that's your container port, not 3000. Okay. And then for this one, just show that it came up on that. Okay, so that is ECS lab number 1. The last thing is the Thunder CTF. I had you do the first one, A1 Open Bucket, so I want you to do the rest of them, A2 Finance down to A6 Container. I hope A6 Container still works, but this had the same vulnerability that I had you in your proxy server exploit that they closed the loop on, so this actually might not work all the way. So if you get to the point where you can't get the metadata, stop right there.